My name is Ethan Harlow.
My name is Jackson Russell. We designed a solar tracker that it's a solar panel that are strapped onto these motors that will turn, and we had these sensors that would detect which area on a little device we had detects the most sun, and depending on where the sun was, the motor would spin the solar panel in the direction to where it would get the most sunlight. It was for UK's engineering program, which was led by Professor Doug Klein.
We basically had a bunch of smaller projects just to figure out what we were doing throughout this class, and we ended up at the end of the year taking all of the knowledge that we had and put it into this challenge that we just had.
All right, we're going to get this presentation started. So what we got going on here is Ethan and Jackson have taken engineering courses all through their high school career, and this particular class is the engineering capstone course. And so they have worked on developing a project, building a prototype, and now they're going to present that to you all today to showcase basically everything that they've learned in the past 4 years in their engineering courses. So they know a lot more about this than I do, so guys, it's on you.
This is our project for UK, the solar tracker.
Sorry.
Good. So the problem we had was that traditional solar panels stay stationary and can only gain a certain amount of sunlight throughout the day, and keeping the solar panels from reaching the max amount of power they can reach from a full day of sunlight. So they're only able to gain however much they can from that same position the entire time.
Our challenge was a teacher prompt given to us by the engineering grand challenge. The final idea would be to have a solar panel that would move towards the direction of the sun so that it can get the most possible sunlight during a day.
This is our chart of just a basic schedule of how we would set up and get this thing built throughout, whether that was getting materials, deciding on which one we were doing, having 3D modeling, printing, building the whole thing, and a wire system, and coding, which took most of our time, to say the least. And end of the Gantt chart here is collecting data and presentation.
We had 5 ideas. This was one of mine. It's a version of our solar tracker that is built on a cylinder that we have 5 photoresistors here, and there's 2 in the back, which are not shown in the drawing. And the way it will be is the sun, depending on the way it goes, the more light detected by each one of the photoresistors will tell the servo motor right here which direction the solar panel, or what degree the solar panel needs to be tilted towards. This was our second idea, and this time I came up with an arch instead of a cylinder. It has the same 5 photoresistors, but this time the servo motor is off to the side, and it would have the same process as the first one.
And this was my idea. I came up with a dome system, so therefore I would have a north photoresistor and a south, east, west, and a center on top. And somehow we would get this servo motor to make this solar panel go in those same directions with the dome system.
This one was my third idea. It would be to have a little cube, a hollowed out cube that we could attach 3 photoresistors to. It wouldn't be that accurate in the end. And it would have the same thing as my previous ideas with a servo on the separate from the cube.
And this was our last idea, and this was also mine. Instead of the dome system, I tried using a treetop sort of thing, so it would get an angled position, so that way the sun would come at it at an angle, and so it'd have it from north, east, south, west, every direction. And yeah, somehow this would stay at an angle just like those and just rotate in the same position.
This is our idea matrix. An idea matrix is what we use to get our ideas down to which one would be the best and the best working one for us. We flipped ours, so it's normally the higher the number, the better the project is, and the lower the number, the worse it is. We flipped it to where lower is the best and highest is the worst. So our number 5.
Our winning idea was number 5, which was my idea for this. So yeah. And we had to change up the design of it because our professor, Doug Klein, suggested that it would be too much sunlight for each resistor considering that there were nothing to divide it. So we added dividers, or Jackson created this 3D print of dividers so that it would block all the sunlight away from it so it wouldn't be flooded or anything like that.
What is an Arduino? An Arduino is a little computer chip, basically, that we can code on MATLAB, and we have different pins that we will connect to our breadboard that will control our components. So we have our volts and our ground. The volts are the power, and the ground is where the power will go after it transfers through the servos. Then we have our analogs. These are the pins that will be controlling the photoresistors, and they will be gathering our data for us. And then we have our 2 digital pins, which are what will gather the data and control the servo motors. And
the breadboard is mainly used for wiring the system, hooking up all of our servo motors and photoresistors, and just regular resistors, just mainly how we were able to set up this whole device. And these were the types of resistors we had to use. I think it was 560 ohms.
Yes.
So, yeah.
This was our schematic. We will go into more detail on each part. The little lines right through here, these are our wires. And over there is our Arduino.
Yep, right here.
And so now the smaller components in here are our photoresistors. We have a north, east, south, west, and center photoresistor. If y'all can't see it, here's a bigger version of it.
This is each drawing they suggested
Yes.
us to draw it for. So.
Here is our servo motors. There is a positive, which is where the power will go. Our D, which is for digital. So that would be going to the digital pin 9 or digital pin 8. And we have our ground. Well, our negative, that will go to ground. Here's our resistors. We used 560 ohm resistors. And
resistors are mainly used to reduce the voltage. So when it passes through, it will be able to contain it all. So, photoresistor. This was the main part of our whole device. Photoresistors' main use is just to gather light values from any light source that you use, whether it's lamps or the sunlight or flashlights, anything. Pretty picture.
this was the servo motor we used, which is what will turn our solar panel, but we had to use an extra power source besides the Arduino's 5 volts, so we had to bring in a 9-volt battery to power it.
Because if not, it would just stay in a certain position and we didn't understand why, and we'd had to push it, and it was just really annoying, so we'd have to use more power for these servos because they contain lots of stuff like that. So this is our solar panel that we used. As you can see on the device, it's a heliocentris. We use these for PoE. which is the second engineering class here at Glasgow. So mainly we use this multimeter which gathers voltage, or I can't remember all of it, but yeah. We mainly use it for voltage, so you'd stick these pins inside of these, the power and the voltage and the ground. So
This was the code we used. It's not the best when transferring between MATLAB and a Google slide, so here's a better look at it.
Everybody understands that?
yeah, right. So basically, we have what is called a while loop for this whole project, and it means like for every time, so north equals read voltage, it reads a different value for each time. Like, it's hard to do this without, okay. So mainly we would use this light source to go towards a photoresistor to get a different light value. So therefore it would, and we have this on display as well, so it's going to display each value that we get. So value here, and then it'll change the value once I leave it, and it'll start going here and getting values, and then everywhere else.
And the if statement here is what controls our servo motor. So what happens is, if north is getting the most or if north is getting the most light, it will change the position from whatever it is currently to the values that are given to it, which are based on the degrees of the the servo.
So that way we have the position in north and south, east, west. So here we go.
Yep, here's our
Show off what we got here. I'll just hit run right here. All right, here we go.
This first part is it resetting itself, so if it's left in a certain position, it'll turn to the north side, and then it'll turn back to the east, which is what we have set as a default.
And right here you see in the command window all our different values of each photoresistor that it's getting. Right now it's getting the darkness setting, so all these values are 0 or a decimal.
So we'll have the sun come up, it'll start hitting.
Now it's in the north.
The values are there, so
it's
north,
getting greater than 1 volt, so that's why it's moving.
and then it can get values from all sides. So it changes. It is on a 2-second pause between data collection, and it will only change after those 2 seconds of pause. South. And west.
All right.
That's awesome.
That is. It's
And
amazing.
we can use this multimeter too by using the solar panel as well, so we can gather data through that as well.
Just the general concept.
Able to see the voltage through the solar panel from the light. So I'll do that. So right now it should be around 3 point something. Right now it's getting voltage from just the air, which is about 170 millivolts. But through the solar panel from the light source, it is getting around 1.8 volts. Y'all
So-
want to come see the multimeter?
So when the-
if you'd want. So yeah, now it is as default.
We have an Arduino, a resistor, and a breadboard if y'all would like to come see it. And here is a servo motor. It's not the same one we use, but is similar in model and design.
And this would be our solar tracker project for UK. Thank you all.
Awesome job.
How long did you all work on this? Like,
We've been working on this since the end of March.
Okay.
Yes.
So
So
it's
let's
a
look.
culmination of all their engineering classes.
Of
that day.
everything.
Yeah.
I think it's just nice to see it work.
It's definitely a relief for how
Mhm.
many times we've had to do this and make sure it does it right. So yeah, being able to show it off and everything and what we've done for the past month and a half, I think just feels like a really good relief.
I plan on going to UK in the fall. I'm getting a major in computer engineering and a minor in computer science.
Well, I don't know where I'm going to go, but I'm probably going to try to go into like pre-engineering or something like that in the nature.
I think it's set me on the right track and got me ready for college.
Yeah, for whatever I go into, I'm sure this programming and knowledge about it will help me in the future.
This is Joe Lawson. He's on our engineering advisory board. Joe works for M&L Electric out of Bowling Green. And Joe started his high school career with me. He was a freshman when I started teaching here at Glasgow High School. And so it's exciting to have him come back and serve on our advisory board and to see what our students here at Glasgow High School are doing.
I thought the presentation was great. It really kind of brings to light the real world aspects of what they learn here and the stuff that they pick up. The ladder diagram, wiring diagram, is almost exactly like you would see out in the real world. So I mean, just the real world aspects of the programming and the coding and the stuff that they can use right out of high school was very, very impressive. It feels good to see how it's evolved. You know, how when we started here, or when we went here, it was a lot of woodwork and it was a lot of, you learn the process behind how to do things. And then now to see how the electronics have been involved in it and the theory and the learning process behind programming and that kind of thing, it's impressive. And I'm glad to be able to see it, to come full circle around like that.
Oh, it's very gratifying. I'm just so proud of him. I got tickled. I heard him say that I might have not known a lot about it, but my gig the whole time I've been teaching is putting students in the best position to learn. If they know more about something than I do, I'm tickled to death with it, and they exemplified that in this project. I'm just really, really pleased and tickled with it.
The way the program is kind of incorporating multiple areas of real world learning is impressive, and it kind of prepares kids for jobs, real jobs in the real world. So I really like seeing that, and I really like kind of the direction everything's going.